Good morning, everyone. Thanks for joining today's Resilient Connecticut webinar to hear Resilient Connecticut tools exploring CIRCA's latest products. I'm Joanna Wozniak-Brown, CIRCA's Assistant Director of Resilient Planning, and I'll be moderating this hour-long webinar, which is a part of a series that CIRCA is hosting along with partners on a variety of adaptation and resilience topics relevant to our state. Before we start, I just want to share a few webinar mechanics just to mention. This webinar is being recorded, and we'll post the recording online following the event. And everyone except for the presenters have their audio muted, but you can use the chat box in the bottom portion of your screen to ask questions. If your chat box is not open, then you can click on the chat icon that looks like a conversation bubble in the lower part of your screen. Simply type in your question and click enter so I can see it as a webinar moderator. We'll try to save the last 10 minutes for Q&A, and I'll do my best to track your questions and facilitate responses with our speaker. So today we're fortunate to have Dr. Yaprak Onet, CIRCA's Assistant Director of Research, presenting on the tools and maps that she and the research team have been working on to create a more resilient Connecticut. Before we get started, remember just to enter any questions you have as we go along via the chat function. Now we'll begin by turning it over to Dr. Onet.
Thank you so much, Joanna. You can hear me, right? Good.
Yep.
All right. Good morning, everybody. So it's been a while since we had a chance to talk, have this kind of a webinar, and it's almost like 2 months, but during the corona time, it kind of changes differently. But CIRCA has been cooking products. We've been working, and we were fortunate to continue our work life. And we would like to give you an update of our recent packages, so how you can navigate that and what they mean. The coastal vulnerability one that we had a chance to talk about it in our last webinar. And I would like to focus, jumpstart on the other product that we have, the storm surge in return interval estimates, and the new sea level rise packages, and then move on to, again, talking about the other stuff and the future events too. So what you see right now on your screen is that this is the Hurricane Sandy National Guard aerial view of the damage. And you can see that the water is coming in on some of the inland areas. So the surge is important part of it, and the flooding is important part of it. And so the question comes to that, what we need to do to plan for the storms. And understanding the probability of any flood event influences the coastal management and the coastal policy making. But what we need to prepare for is a general flood level. And how we are going to decide on a flood level is we need to know the total flood level. That is the combination of the storm surge. Storm surge is due to a water rising up due to the pressure difference that hurricane creates and then piling up on the shoreline. The waves that's coming up due to the disturbances created in the ocean, tides, and river flow. So the product that I'm going to talk about the rest of the webinar is going to consider these 3 elements: storm surge, waves, and tides. The reason that I am talking about all these 3 things, first, we are going to focus on the general ocean model. And then the second part of our products in our, hopefully, future webinars, we are going to talk about the nearshore modeling, when that's going to integrate both ocean and the river flow. So right now, we will have all these information that's going to be presented for you. And I would like to talk about why we are doing this. Yes, they are FEMA firm maps. They represent 100-year flooding for the all the coastlines of the US, and they also represent 500-year floods. And FEMA's approach for estimating floodplain maps includes a regional statistical approach. They apply it to Bridgeport, New Haven, and New London tidal stations. What you see on these maps are tidal stations from NOAA that's available. And they use these tidal stations to apply a probability distribution data to these gauges. And that's how they estimate the storm surge. And the wave is they use the Tweed New Haven Regional Airport wind data, historical wind data, and obtain it in the open boundary in deep water. And then they have the transects that you are probably all familiar with. and that they move the wave data in the deep water along these transects to the shoreline using empirical equations. So one of the drawbacks of this approach is that storm surges are interpolated over only 3 stations. And what you see are the data available for all these stations that you see. There's Montauk, New York station, and there's also Kings Point, New York station. But except for the New London, the data is pretty recent. It is what it is that we have available, but if you just interpolate it along these 3 points, that's going to give a little bit false representation in some of the parts, like here or here. So what is going to happen in these towns over there? And the calculated incident wave heights also don't really consider refraction, diffraction, and bottom dissipation. So it is done in early previous years. So therefore, a downscaled and more comprehensive understanding of total wave elevations can help us to assess the risk, and therefore can help us to understand and design the costs and environmental impacts for the coastal plans. So for that reason, we did this annual exceedance probability analysis or return period analysis in Long Island Sound to update at a higher resolution. And for this case that we provided the storm surge values and the significant wave height probabilities to aid the engineers and planners and develop a cost-efficient design criteria for resilience projects. So I'm going to talk a lot about the Long Island Sound model. And this is a model that we developed here in CIRCA with Dr. Chan Liu and Yan Jia. So this is the boundary of the Long Island Sound, the color-shaded one that shows the bathymetry. And what we have here is that we obtained the wind information from the yellow airplanes are actually the airport wind data locations that you see. We interpolated this waves bilinearly in 2D structural environment with a horizontal resolution of 0.02 degrees. And we not only just depending on these winds, we also calibrated them with what you see here is the red triangle buoy stations, because buoy stations has the weather information as well. And we actually calibrated that so that it will not give over and underestimation and actually give the correct validation with all the buoy, tide, and sensor information. And in addition to that, we use the model that we use is we frequently mention FVCOM. It is finite volume commuted ocean model. And we coupled this with a wave model, which is SWAN. So the resolution that we have in deep water areas can reach up to 5 kilometers, but along the shorelines, that's going to be around like 500 meters. And we also included the tides in this model. So what you see in these blue stars are the locations of the estimates that we have for our model results. We use the highest 44 storm events. The reason that we started from 1950s, because that's the most oldest available data that we have from wind stations till 2018. You can see the list of all the events that we actually choose. The reason that we wanted to choose 44 storms is because that we wanted to use a threshold. If you include like very small events, then you will not have a good representation of the extreme storm projection. And that's the reason that we actually use a threshold to see for each stations and observe all these historical events and do the projections for the future. And we validate our model also with the buoy stations, the 4 triangles that I showed you, tidal stations that we had, all the 5 ones that I showed in the previous slides, and also the USGS storm sensors. And you can see that it aligns with the peak and the time very well. Some of the times that it doesn't have the down peaks, and that's because the station was on the dry land. It didn't have that much, but it reaches the peak of the floods quite well. So you can trust our model in this sense. And I'm going to talk about quite a lot of the annual exceedance probability, or what generally people use return intervals. So when we have all these informations in the blue stations that you see, blue stations, we have the water elevations, and then we recorded them here. So then we rank them from highest to lowest. So this event has the highest elevation. So that's the first event, the highest event. And the second highest is this event. And the third highest, fifth highest, fourth to fourth highest, and the last one. So when this rank is done, then you calculate the probability. The probability is this rank, for example, 8 over how many events that we have, like 44 events, 44 plus 1, 45, and that is the probability. So what this represents is the annual exceedance probability, which refers to the likelihood of flood event occurring in any given year. So there is 11% probability that this event is going to happen. What generally people use return interval is 1 over probability. So this is the 9-year return interval. This also refers as a recurrence interval, and it is based on the probability that a given water level will be equal to or exceeding any given year. So what I want to talk about that annual exceedance probability is generally people use return period, but return period is a little bit of misleading because it enhances the possibility that we can predict the future. And if a period of flood occur, we might have a security period that storm happens again. Or even that the major flood not occurred for some time, we might have a more occurred in the future when it happens. So let's say that when we have a 100-year event in 2020, are we going to have the next event in 2100? This is completely a false representation. And that's because storms don't have some kind of a schedule. Every year, so when there is like a 100-year flood event that happens this year, the next year, there is a 1% chance that the 100th flood event is going to happen again. And that's the reason that we use mostly annual exceedance probability, AEP, and that's also now adapted to all the coastal engineering fields too, because this return interval is giving the false representation. But in our products, we use both terms to reduce the confusion. So now we have our products. What you see, the water elevations that I mentioned, all these water elevations here, are represented in blue dots here, blue dot elevations. So when we have all these blue dots, and you can see the thresholds, like it's going to be very, very small. So we represent all the elevations and we represent the corresponding return period on that elevation. And if you can see that there is a gap for the events when they are very high, because strong events don't happen that frequently. Like I said, like a 100-year flood has 1% chance of probability of occurring. So if you would like to know when there is a data gap between like 70-year event or a 50-year return period event or 2% chance annual probability, then we need to fit a line here. And that's what we did is Poisson generalized Pareto distribution fit. That is a asymptotic distribution that's generally used to represent extreme values over a threshold. And that help us to form a more general extreme value distribution when it combines with Poisson distribution. So what it produces is the best fit among all the generalized value distributions. We saw that our results of the empirical distributions between the buoy observations are very small because it fits very well. And that's one of the reasons that we choose this fit in this information. So you'll see in our viewers these images quite a lot. And one of the things that I want to mention this is that, okay, we have the fits and you'll have all these numbers in between too. But just because that something happened like Super Sandy storm, we wanted to mark that, and the Irene, that's one of the common ones that's remembered. It depends on the location. You can see that in New London, Sandy was not a 100-year event. It was even close to 30-year event. The highest 2 points that you see for Sandy are, for New London are Hurricane Carol in 1954 and Great Appalachian Storm in 1950 November. So representing that all the historical data was important for us to develop it. But on the other hand, when you look at the Bridgeport, you can see that the Sandy was close to the 100-year event. So the location of your flood return interval or annual exceedance probability changes along the Long Island Sound. So now we go to our website. I wanted to show you what we have available for everybody to use. So this is our main website, and you click on the technical tools and it opens up. So in our page, we have different categories. You have projects, you have data viewers, documents, and data sets. So we wanted to organize it this way. If you have a purpose to just go see the data sets, then you can go click and see all the data sets available. If you wanted to see, just play without all the viewers, you can go to them. If you want to talk, read a little bit more about the information, then you can go. There is a small, short information with the important notes on it, and you can read more about it for each project. So that is the navigation through our website. But since we're talking about it after this webinar or during this time, that you may think about, I want to reach all the information about one project. And that's why we have this project part. So the annual exceedance probability project that we talked about this year. So let's examine everything together. First, we have an annual exceedance probability viewer. In this viewer, you will see that there is a map part, and there is like this empty part with a drop-down menu. First of all, in this map part, you're going to see that there is a representation. Actually, all of them are clicked. It shouldn't be. There is a representation of a total water elevation, meaning the summation of the surge and the wave. Tides are already included in the model, so you don't actually need to add an extra tide onto this. So you are going to see the distribution of that, and for each point, and you will be able to reach the information for the depth and the location, and also the elevations for the 2-year, 3-year, 4-year, up to 100-year flood. And you can see the distributions for the general 100-year flood, significant wave height, and storm surge. The second part is where you want to reach your information about each town. For example, I choose Brantford. I can see that there is a return period represented here. And H and HS, if you don't know what it is, don't worry. Here, the data description is represented here. They represent the storm surge level and significant wave height, respectively, in feet. So we come here. I'm sorry that it's written meter. I will correct that. That's a typo. But you can see that for 100-year, it's going to be 8.32 feet and 14.5 feet significant wave height for Brantford. And the depth is 30 feet. So you can also see the graphs that we mentioned about it. And let's say that if you want to compare, because we mentioned that the location is different, right? So depending on location, your values can be different. I can compare different towns. I can compare Bridgeport. I can compare another Clinton with each other. I can see their values, how different it is. And I can see their graphs, how differently it can represent. If you would like to have a comparison of only just 2 towns, you can remove the town. Another thing that we talk about during this time is a town package. This worksheet is a part of this town package. So you have, let's say that we write here Brantford, and there's an information about the annual exceedance probability and return period. And then this is a sheet to help you to work through this website. So you write here, okay, what is the annual exceedance probability of the event? I want to, let's say, the design for 100-year storm. So that's 100 years or 1% exceedance probability. Then you can come here, second part. This link goes back to here. And you can see that, okay, for 100 year, what is it for, what is my elevation, storm surge level, and significant wave height for Brantford? Let me go here. Go to Brantford, 8.32 and 14.5. I'm going back here, writing that information into the table. And then I come here. What is the lifespan of the project? Depending on your project that you want, it's minimally, we suggest like 30 years, but it depends on the design. Let's say it is 30 years. And now you consider the sea level rise scenario. So we are in 2020, for 30-year project, we need to design it for 2050. So you basically add the 30 years to the current year here. And then you're going to choose the minimum sea level rise scenario that you want your design to happen. So for 2050, CIRCA does the suggested planning threshold of 20 inches. But if you would like to do different scenarios, you can use this graph. So if you would like to plan for a high scenario, medium scenario, medium high, or medium scenario, you can use these different values and read it from this graph, that what it corresponds to, meters or feet. And this is the information that we put it here. Then deciding on the design elevations. Here, to storm surge level, you need to add what you have for storm surge plus the sea level rise information. So what we have for Brantford is 832 plus 1.67, which is 20 inches, 10 feet. With respect to NAVD 88. NAVD 88 is National Vertical Datum 88. That's so all this 10 feet, it's not from where you see your ground is, it is based on the NAVD 88. And so we have actually a representation here. You can have the NAVD 88 if you want to know where you can get the NAVD 8, like the height information for your location with respect to NAVD 88, that we suggest to use LiDAR information. And for the design, just because that you have this much storm surge level, that doesn't mean that this is your design level. You may consider it for the first floor elevation or base floor elevation to do that. So the first floor elevation is the summation of base floor elevation, which is commonly used by FEMA to define the 100-year wave crest elevation, plus the freeboard level. What you are going to use for base flood elevation and the 100-year elevation, it's written here. And for the freeboard for Connecticut, it is suggested to use an additional of 2 feet. So you can know the storm surge level here, and you can calculate your significant wave height level here. As an example, it's calculated. But that doesn't mean that this is your final design. Depending on what kind of a project that you're doing, your total water elevation is going to be the summation of those two, but the engineer firm can give you, or like the plan that you're gonna have can be higher, because in engineering projects, we also consider the factor of safety and other base flood elevations and the freeboard levels too. So that is the reason that we are just guiding this through using this toolbox. We did this worksheet, but the final design is going to be specific to your project. That was the viewer, and this worksheet is a part of a town package that we talk about. Now we have all these, before we go to this one, I want to actually come to that later. We have a little bit of documentation. And all the short summary of what I'm talking about, the technical information is here. We actually write an article on this, and it is in a peer-reviewed journal. So when it is published, it's going to be open access, and this information is going to be updated. So if you would like to have the data set yourself, then you can come here and you can click on and have all the town information for different flood levels. Another update it's going to happen to this data set is that we are going to publish a netcdf file for all the 44 storm events, that so that you will have the water elevation and the wave elevation for any kind of a location in the Long Island Sound boundary that we have. But that's going to come next. So another thing, okay, so I'm going to come back to those later. So I'm going back to my presentation here. We talk about all these graphs and everything, but we talk about also the sea level rise, and why we are using the sea level rise is because, for example, I'm reading this 10-year flood information here. It's almost like 2.1 meter. And then I added, when you have this information, this is the 20 inches of offset that we are using. So I duplicated this orange line to this green line. And the difference between those two lines is the 20 inches or 50 centimeters. That is representing the sea level rise. So for that, the same number that I reached, like 2.1 meters, that I reached for 10 years, is I reach it during almost like 3 years. So this is another important, very important result of the sea level rise. Just because the 20 inches is may not be seen that high, but it is also impacting that how frequently you're going to see the events. So currently you're experiencing 10-year flood. You're going to experience that in 2050 every 3 years. And that's going to change quite a lot your design levels. That's why you need to consider sea level rise information. It's going to also impact how frequently you can see your 100th year, how frequently you can see all these things, all these information. Another product is the sea level rise viewer that we added to that, and I'm going back to this. So we have now in our sea level rise viewer, this is the one that you are probably very familiar with, and you can write the information for where if you're looking for a specific place. And in this map that you have, here are the layers. So you are familiar with the mean high water and these NOAA projections that CIRCA calculated already. These are calculated using the 3 stations that I mentioned you. And all the tidal stations actually we interpolated that. And then we find the storm surge values along the shoreline. That's similar to the FEMA approach. But now since we have the model, you can actually click on the FECOM version and you can see that what would be the extent of the 10-year flood event, 10-year flood plus 20 inches, or you can see that 100-year flood event and 100-year plus 20 inches. Another example that we are going to, in addition, that yes, you can see that. And these are based on LiDAR information, so the resolution is very high, 1 meter. And the next update that's going to come to this viewer is that when you click on it, you'll be able to see how much flooding that your land is going to experience, approximately. So that's going to also be done during this viewer. And if you would like to reach those maps, you come to the data set, there is actually GIS layers available here, and you can reach all the information and the updated times for these layers. So that is the storm surge, and you can reach storm surge map, and you can reach them from different various data sets too. So let's go back to our presentation again. Okay, so the next part that I would like to talk about is the Coastal Vulnerability Index model. I'm going back actually on the website because we had quite a lot of talk about this Coastal Vulnerability Index in our previous webinar. So if you would like to go to that information again, we have a story map created for you. And you can understand why the reason that why we are doing the coastal vulnerability assessment and what is this model. And then the reason that we developed this model, as you can see that for the reds, these are the hotspots that we need to put our resources in or try to understand by clicking on them, that what is causing actually this redness and how we can actually look at this in regional or local scale. So this allows you to do a multi-scale assessment. So if you're looking for just like natural habitat vulnerability, then we have an index for you prepared in that sense. And the methodology, just to summarize it, we have all the available data that's also open access, and we digitized it and ranked it from considering that 0 to 20 in the quantiles, and 0 to 20 can represent very low, and vice versa is like 80 to 100 can represent very high in that index. So you can see that red is bad, but green is good. And then we are going to 3 sets of analysis. And actually, I can go to the website to look into this. And then we also, yeah, I will talk about this on the website. So I think it will be just easier. All right, this is our website. This is the coastal vulnerability viewer. And one thing is that if you can get lost of how to do this or don't want to listen to me again, you can just go to here, the guided tour, and all the citation and data disclaimer is here. So it just guides you through how to use every little thing that I'm going to mention here. So you can do the analysis in Connecticut scale, or you can choose a custom extent and actually arrange the boundary of your analysis. Or you can write it, type it here, or you can just choose a region that you want to type, like let's say New Haven. Let's go to New Haven. And you can see this information. Okay, so the assessment type is under 3. The first one is the contributor layer. This is just an individual layer. It is not overlaid with any kind of a climate stressor or anything else. And what you're going to see that in here, layer info, what layer that you're looking for. You can go to the contributor layer selection. So we are looking for absence of personal vehicle. This is that in every house, the household that doesn't have any cars, that's represented. And how we are ranking this from red to green to yellows, it is given here. And you can also see that the empty ones just represent that there is actually no data available for that area. So if you want to go a different layer, you can type it here again, just to show you. You can see that for this layer, and every square represents actually a value. The reason that we ranked it 5, it is the real information is 10.7 feet. You can come to that table and look at that, where it goes into. And you can see here in this distribution, this is like a statistical distribution. Each little square represents an acre. And you can see that that's therefore a number of grids or acreage, that you can see how frequently you have this information. For this little area, I want to click. Okay, it actually shows, but I'm not sure why it's not showing right now. Of course, it's not showing right now because I'm broadcasting this and it wants to humiliate me. Anyway, so you'll see that the percentages, here we go, 14% is between these 2 ranks. So you have this all information. And then you can have the mean rank and the general statistical information, that how much data how many acres of data that you had, and the total acres of the study area that you have. You can also go to the download and want to know like where we get this information. The source link opens up and go back. And then you can download the metadata that we have available for this information, or the GIS layer individually, this information. This is the whole list. It's almost like, I think it's 47 layers. A lot of layers are available here. So you can just see that, like how it's represented in closeness to healthcare, everywhere. And the second assessment type is the vulnerability layers. Vulnerability layers are overlay of multiple layers. And you come to this selection when there is a vulnerability right next to it, social vulnerability. Then you'll see that that this layer is, we consider the sea level rise. We overlay this with sea level rise because we consider the sea level rise vulnerability here with all the different social layers. Or you can go to another layer, let's say erosion vulnerability. Here we go. What we laid on is sea level rise, shoreline change, erosion susceptibility, all these layers that we overlaid with. And the distribution, that you can see that. And you can go to downloads. Since we created this, there is no source for that, but all the metadata information where we get all this information, and the GIS layer is here for you to download. Another thing that you're going to see is the sensitivity, exposure, and adaptive capacity layers. So we consider another term, vulnerability layers that's created all here. They are equally weighted on top of each other. But we wanted to give an opportunity for any kind of a stakeholder to play with or arrange it and reflect actually better. So fine tune the vulnerability in that area, but giving an option to weight. So explore the trade-off capacity. So that's why we have like exposure, sensitivity, and adaptive capacity terms developed. So for all these three layers have their subcategories. For example, sensitivity has a build sensitivity sublayer. What sensitivity is written, explained here, and what build sensitivity is just like the build likelihood of changes in the built human systems. This doesn't have any climate stressor on it, so it is just a combination of railway, cables, buildings, infrastructure. So if you would like to consider and just specific climate stressor, like just flood layer, you can download this and overlay with the flood layer, and you can see that the results, like how the index is going to change, and the index distribution is given there. Likewise, we have climate exposure. Actually, if I go to this part to represent this weighted opportunity, it will look better. So for exposure, we have climate and non-physical exposure, which means that the exposure is generally due to a non-climate related. For physical, it's a non-climate related. And for climate, it's all just like climate related. So we have everything here: sea level rise, storm surge, tidal, wave power, wind, and sea level rise, everything. And for the physical layer, these are the things that's considered for the exposure. These are or just due to what is already there that can compose a risk to you. So if you would like to see the change in the distribution, you use this bar to see how the change, if you increase the weight of the climate exposure, how it reflects, and whereas if we increase the physical exposure, how it reflects. So the reason that we wanted to give this as like a communication to the tool to the public, and also to see if the representation of your vulnerability map that's going to provide it by just like equal weighting is not really explaining the vulnerability in that area. It will give a user a chance to see like what how they can play with it, and also say that, okay, what we need to do. For example, let's go to the general. These are the subcategories. Now we can go to the general one: exposure, sensitivity, and adaptive capacity. This is the vulnerability of New Haven that we see it. But you may think that, hey, this area actually
we lost the audio for a second.
Oh, okay. So which part do I need to go back to? Maybe this trade-off that we are mentioning that. So for the trade-off, so you can increase this layers, and then you can show that by decreasing the map needs to update it better. Okay. How increasing the adaptive capacity or decreasing the adaptive capacity is going to reflect in your area. And let's say that if you want to overlay it into a different map, you can do that. And if you would like to overlay it to a flood event, then you can do that with that viewer. And if you have a different audience that you want to represent in different colors, you can do that. And then you can also do a solid coloring or transparency arrangement. So this may be a little bit too much to navigate for different users, because like it requires an analysis, and then you can go actually click on every cell and then understand what is the background information that's contributing to the vulnerability in that layer. So in our town package, we also planning to provide like some kind of a report to explain for each town what this means. Also, if you are a GIS viewer, a GIS user, and would like to play with these available ones and see what to do, this is the index dataset available. You can click here and also know like what is the time coverage, spatial and temporal resolution for all of our information, and the source links that we have. You can reach them from the one place. And you can come here, and instead of going through the viewer, you can actually click all of them one by one, or you can just click this one and download all of it. You can click summary tables and download all of it too. You can just click individual layers, or you can click on the source layers to obtain where we get all this information, and all the GIS information too, that's here. And all the map packages are presented here too. So you can just click them and then download the map package and then play around with that too. So I go to the viewer, I go to documents. Okay, everything is done. So next part is that what we have is coming soon is zones of shared risk maps. So for the zones of shared risk in our previous webinar, we talked about it. There are 5 sets of maps are prepared for each 14 towns. So they are the topographic maps. That's the combination of slope, contours, and watersheds. There are the flooding projections for these maps, and they are also structure and roadways, sewage, and the future projects that's going to happen, and the key buildings. Ecological systems, and also land uses and social characteristics. All these 5 maps, this one, and the previously 3 ones, are combined to draw zones of shared risk map. Our landscape architectural team is working on to identify which will be the zone that's commonly facing the challenge from these things. What we are going to have is a data set available for you to download all these maps in PDF format, and also the viewer, so that you can click on and off, and then you can overlay it. And we are going to do, our next analysis is going to be combining the zones of shared risk with the vulnerability maps to see how much we can fine tune for each area. Our landscape architectural team is also working on looking for the cross-jurisdictional boundaries. So meaning that between 2 towns, 2 boundaries, like what will be the places that or the key structures that's going to be flooded. And that's going to be the next product that's in June that we are hoping to publish. And also I mentioned about it in the beginning that for total level elevation, we have now storm surge, waves, and the tides, but not the river flows. So next step is the Nearshore Model, where we are going to use our FVCOM model to obtain the boundaries here, and combine it with the inland flow, river flow, to model it in a more higher resolution, to give more accurate information for each location in the shoreline. So that's going to be another product that we're going to have. So these are all the updates that I would like to talk about it for now, but you all aware of the resilience roundup, so that's going to be monthly updates. But if you want to know whenever we have a change or some kind of layer update or a data correction or anything, we are going to publish that on our Twitter account, so you can follow that for more recent updates as well. This is the end of my presentation, and I'm actually very happy that you're here and listening to me. So I think we can ask for questions now.
Thank you, Aprak. That was wonderful. And I appreciate you plugging the Resilience Roundup and the Twitter feed too. That was wonderful. It's perfect. Well, we got a couple questions here. One question is, how frequently is CIRCA planning to do updates on the data sets?
That's a great question. So for the return interval one that we have available every 10 years. And if you actually have a question for a specific viewer, then you can go to our datasets. And then let's say we come here, there is an update schedule. And that's how we are going to do. But the Nearshore model is going to be updated probably end of summer. That will have results available. So next fall, that some of the layers are going to be updated. The flood level, sea level rise. This one is this one is going to be updated in the next month also. So these kind of stuff for every 10 years that we need to do a flood analysis, that's going to be every 10 years. Vulnerability assessment, it's going to be updated with the new census coming up. And also we had every social layer in track scale, and now we actually obtained them with the block group scale. So that's going to be an update next, that's going to happen in the summer. So that's going to be frequently, but other than that, the vulnerability assessment depends on like how frequently some of the layers are going to be updated. So I would say that every year that we will look for it and then see if any layer is going to be updated so that we can change all of our analysis. But other than that, yeah, the maintenance is yearly for every data set that you see, but the updates for the specific ones are like maximum every 10 years.
Wonderful. Are these hosted on an ArcMap server or ArcGIS server so that if somebody's connecting via server that it would be updated?
So in the data sets that what you have are just like maps and map packages. They're not connected to a server yet. But actually this is a good idea. We can do that. And that's why I would like to have this like feedback session too. Yeah, sure. Why not? We can connect to the ArcGIS server too.
Okay, we have another question here. How is CIRCA planning to use exposure, sensitivity, and adaptive capacity weighting?
Okay. So the thing is that we are in collaboration with Center of Government, and we are having the data set updated from them. So there are a couple of ways that we are hoping to incorporate this. One is that with central government feedbacks that we are going to tweak this information. There is actually a methodology that we follow, so it's not just based on our minds. It's an expert opinion are based on an analytical hierarchy process. So we made the we give like a surveys and then collect those survey answers and it distributes a weight scale. So that's kind of the first feedback loop that we are hoping to get. The second one is that we are working with a contractor, and for when we are doing the regional assessment, that when they have the town feedback, that they can be tweaked. And the third way that we can do this is when everything opens up and then we have a chance to interact with the towns, then we can have that during that town meeting to get feedback on their perspective, to reflect that into the maps and then weight that. So we have plans. It just depends on the cogs are going to be the initial one that's going to happen, but the other ones are depending on most of our current situation, actually, how much interaction that we can do and engagement possibility.
All right, thank you. Are there any trends evident in the surge and wave intervals along Long Island Sound?
Yeah, actually, you can see that. Let's see. There we go. So let's see this 400 here. You can see that the storm surge, oops, elevation is higher in the darker points. Elevation is higher on the western Long Island Sound. One of the reasons that is that winds generally, like the hurricane winds are generally below, it depends on its direction. There's a long fetch in the Long Island Sound, and this just allows wind to build up water levels along this area because there's not really a discharge opportunity happens in this end. So that's the reason that the storm surge values are higher in western Long Island Sound. If you want to look at for the significant wave height, you can see the darks are along the mostly on the eastern part. And one of the reasons is that you can see that eastern part is open to ocean, and it just takes more waves, and it also has like impacts coming from the continental shelf. So the significant wave height is higher on the eastern side of the Long Island Sound. But the total, it actually just like depends on like this is kind of distribution. It just like rises, lowers, because it's the summation of both.
That's really interesting. I can see how that would play differently when you're designing infrastructure or different engineering for the different water events.
Yeah, exactly.
Your location. Yeah, that's interesting. We had another question here. Just a reminder, folks, that if you have questions, you can enter them in the chat box. We have a couple more minutes here, so we could take a couple more questions. The question is, did CIRCA have an opportunity to compare results with the Army Corps NACCS project results?
Yes,
the water levels?
We did, definitely. Yes. And the thing is that the NHCC's Next Study there are some overestimations and underestimations in some of the parts. Let me see. Give me a second. Okay, so in Next Study, it's generally like an overestimation of the water level. However, the differences are somehow reduced in the central sound, like especially between like Fairfield and Waterford. That's kind of what we see in most of the time, and they also overestimate a little bit on the significant wave height too. So we have actually plots that's comparing the next study with our plots, and that is going to be published very soon. So maybe, hopefully, very soon. We did the comparisons. I can just show it to you. Okay, return. These are some of the results that we had for the return period of the light blue ones are the NAC mean, and the shaded one is the 95% interval. And this is our line.
Do you mind zooming in a little?
Yeah. Okay, for Bridgeport. So it is not that much, but there's a little bit of overestimation. This is just for the water level for the 3 stations. And I'm going to show also significant wave height. And it's a good thing that they are in the 95% interval, our results with them. And this is kind of an observation that we have with the comparison. There is not really so much big difference, but NAC is using a rather bigger scale. So that would be one of the reasons. And also NAC is using for the different synthetic storm events. And some of them are not really resolving very well inside of the Long Island Sound. When we were doing the wind data analysis, we actually had to do a lot of calibration with the buoy measurements and then the airports. And that's one of the reasons that we use those information, because even the WRF weather station, weather regional forecast model, it was not really, the initial results were not really supporting simulation before 1979, and the analysis that was covering it was lack of resolution. It was not really fitting the information, like the buoy results, real-time results. So we actually had to go through a lot of like calibration to fit our model, and that is probably one of the reasons that Next Study and ours are not match to match. NAC is still good. We are still in the 95 percentile range, but because it was using a different storm levels and synthetic storm projections, and then looking for a larger scale, that would be one of the reasons that there is a difference in the results.
That's great. I think we've accomplished most of the questions that came in. If anybody has any last minute ones. Somebody did ask if there will be a recording available, and yes, we posted on our website and also our new YouTube channel. So we should you should subscribe to that to make sure you get a notice when we have new videos coming up. So it looks like there aren't any more questions coming in. So I wanted to make sure to give a warm thanks to Dr. Onat for her time and expertise today, and all of our attendees to coming. I know it was at the tail end of a holiday weekend, but we appreciate you being here, and I hope that you have a wonderful rest of your day.
Thank you so much for joining us.